Fora TV. The world is thinking.
Welcome to the last session in the science strand for today. It's got a great title. Particle Physics is Sexy. I believe that. We're a little late, so I'm going to rush through the introduction and get us into discussing what we mean by particle physics and is it actually on the way up? Is CERN going to attract more people into studying physics? Or maybe is the way that science is going meaning that we're going to witness the end of big physics when CERN launches the Large Hadron Collider? I think they're going to fire it up in May, is that right?
Hopefully.
And will there be anything to replace it after it's finished its useful purpose in the next couple of years? Who knows? Right, I have two speakers on this one. Brian Cox, and Brian, on my left, is based in Manchester and CERN, and he's in charge of part of the project there to upgrade CERN, in charge of two of the detectors there for the Large Hadron Collider, which is, I'm sure, well, if you know a bit about physics, it's looking for a mysterious particle called the Higgs boson, which maybe Brian will explain to us. And Brian's also a television and radio presenter, and he's been involved in programs like Horizon, the Large Hadron Collider, and Einstein in 2005. He was also famous for being a keyboardist for a band called D-Ream, who produced Things Can Only Get Better in 1997. Not sure. Right, okay. Then on my right, I've got Joe Kaplinsky. Joe's a science writer and researcher, and he's carried out research in low-temperature physics, and more recently he's working in biophysics. He's been a patent analyst in various fields in technology, and he also contributed a chapter on Chernobyl and nuclear power to a collection called Science versus Skepticism, the Case for a New Scientific Enlightenment. And there we have it. So without further ado, I'm going to let Brian go first. I think he's going to talk for nearly 10 minutes or thereabouts, and then Joe will go, and then we'll throw it out to the audience. Any questions, and we'll just see how we go. Brian, thank you.
Thanks. Tony Blair isn't my fault, I should say, even though Things Can Only Get Better was my song before we start. I just thought I'd give just a very brief introduction to what particle physics is and what we hope to achieve with the Large Hadron Collider at CERN. So really simply, particle physics is the exploration of the world of the small. I suppose that's the easiest thing to say about it. And what we found over probably about 100 years, you could argue, since Rutherford discovered the nucleus, is that everything we see around us in this room can be made of just 4 particles, actually. In fact, 3 in a sense. 2 quarks called an up quark and a down quark and an electron. So the protons and neutrons in your body are made of up and down quarks. The electrons go around there, and that's atomic structure. So an incredible simplification. We've also found another 2 copies of those particles, which is rather strange. So there are in fact 12 fundamental particles of nature as we know at the moment. The copies appear identical in every way. So the electron has got a partner called a muon, and the electron has also got a partner called a tau. They're heavier, but identical in every other way, and we have no idea why those copies exist. We have a interesting, from measurements made at CERN actually in the 90s, we believe that there are no further copies, with some very small caveats that appears to be true. So why nature is built that way? Why does that pattern, 12 particles, that allow you to build everything in the universe, 8 of which appear to be essentially useless, but they're still there? We have no idea. That's one of the big questions. The other fundamental aspect of particle physics is to describe the forces of nature. So that's the way that those particles talk to each other. And there are 4 fundamental forces, as we know at the moment. There's gravity, of course, which is the oldest known of the forces, in that Newton first came with a decent description of it in 1680. And actually, to this day, it's one of the big issues about how we bring gravity into our picture of the other 3. And that's another thing that maybe we'll get to talk about, that the LHC is, well, high up on the LHC's menu, hopefully. The other three forces are forces that work in the subatomic world. So there's electromagnetism, which kind of I suppose everyone's familiar with, fridge magnets and electricity. There's a thing called the weak force, which allows the sun to shine. And for the more, if you're scientists out there, then is responsible for radioactive beta decay. And actually the weak force itself was only understood in some detail, or the experimental verification of our picture of it in the mid-80s. So a very, a force that's not been understood very long. And then there's the strong nuclear force that sticks the nucleus together. By particles called gluons, the unimaginatively titled gluons. So just to really summarise, I suppose particle physics is the study or the search for the ultimate building blocks of the universe and the study of the forces that make the universe work. Really, in modern physics, the picture is that for anything to happen in the universe at all, a force has to act, and we've narrowed it down to about 4. So the LHC, that sounds like essentially a complete picture apart from these families. But there's a series of enormous questions. In a sense, I feel that the wheels are beginning to come off our picture of reality. It almost feels like at the turn of the 20th, the 19th and 20th century, when people thought they'd understood all of physics, and little cracks began to appear. And there are some quite serious cracks actually beginning to appear in our cosy picture. And this is why the LHC has been built and why it's as big as it is and why it's got the energy it has. One of the first and I would say guaranteed discoveries, it sounds unscientific, but I could explain it if anyone wants to ask a question. But I would say it's guaranteed that we'll understand the origin of mass in the universe. Right? From the studies that we've done throughout the last 20 or 30 years or so, we've seen that all our equations that describe the forces and the particles of matter that we've found over the last century break down at the energies lower than those that are collided at the LHC, so below the LHC energy, if you don't have an explanation for the origin of mass in the universe, which sounds like a very profound and simple issue. So the Higgs particle, which I think you just mentioned, that's our best guess, or the simplest guess, for the origin of mass in the universe. If the Higgs particle exists, then you find it at the LHC. If it doesn't exist, and nature has a habit of, confounding us and surprising us, then whatever does its job turns up at the LHC. And that's really the reason, one of the main reasons the LHC was built. But there are other huge and fascinating questions which I'd be more excited to see answered. One is that it turns out that 95% of the universe is made of something other than those 12 particles. So that really, over the last 10, 15, 20 years, we've found that our beautiful picture of 12 fundamental particles of nature doesn't describe most of the universe at all. And it's true to say that we have very little idea what the other 95% is, which again sounds embarrassing, but it makes it incredibly exciting. 25% of it is in the form of something called dark matter, which we see by looking at the way galaxies rotate and the way that the universe on the large scale moves around. And an even more baffling 70% or so seems to be in the form of dark energy, which is a kind of bizarre anti-gravity force that pushes galaxies apart from each other, is accelerating the expansion of the universe. Again, a huge mystery. And the final issue, which I think may have some bearing on that, is just understanding that oldest of forces, gravity, the force that Newton described and Einstein described in 1915. Einstein's description, by the way, is the best description we have of gravity. It's such a weak force that it plays no role in particle physics. In fact, it's, if you pick a glass up off the table, you can tell how weak it is because the whole Earth is pulling it down and you can just pick it up. The weakness of gravity is one of the biggest mysteries, I would say, in fundamental physics at the moment. And again, there's some ambition that if nature's set up just right, then we might get some signposts as to where to go in the understanding of gravity. String theory, by the way, is an attempt, I know that was in the introduction, string theory is an attempt to understand gravity, but it shows you how difficult it is because no one's been able to do it yet.
Thank you. Joe.
Okay, thanks. I think that's a kind of really nice introduction to some of the things that people are trying to get out of the LHC, and I think if you look at kind of the excitement generated around the LHC, you can see it's clearly inspiring, certainly the kind of people who follow along with these sorts of developments. There's a kind of real anticipation building up. But I do think that there's a bit of a broader problem in terms of the appreciation of particle physics and, really pure science and the investigation of nature for its own sake in society. And I think even to the extent that this might kind of raise future problems in terms of the kind of large resources that kind of have to flow into these projects, I think it's kind of quite important that we try and stake out a case for the significance of this sort of work. Not to kind of bring the mood down too much, but I think we can maybe remember that although the startup of the Large Hadron Collider is kind of a wonderful thing, all the way back in 1993, we already had the cancellation of what would have been an even larger particle accelerator, superconducting supercollider in the US. And the kind of explanations that were put forward around that were kind of to do with budgetary mismanagement and so on. A few people did kind of try to look a little more broader than that and look, well, the end of the Cold War, people aren't so much interested in kind of investing for kind of national prestige and so forth. And I think that we do have to kind of investigate these things a little deeper and perhaps look at them as a bit of a warning. I don't know if people are familiar with the online satirical publication, The Onion, which bills itself as America's finest news source. I can highly recommend it as a great source of reading. I mean, like all great satire, it does tend to kind of cut to the point sometimes. And on 28th of September, a couple of weeks ago, they ran an article headed, "Scientists Ask Congress to Fund $50 billion Science Thing." And I won't read you the whole thing, which is worth looking up online, but I'll kind of give you a couple of key quotes from this article. So on the one side, you had the quote, "While expense is something to consider, I think it is very important that we have this kind of scientific apparatus, because, in the end, I have always said that science is more important than it is unimportant," Committee Chairman Representative Bart Gordon said. "And it's essential we stay ahead of China, Japan and Germany in science. We're ahead in space, with NASA rockets going to other planets, so we should be ahead in science too." Right? Countering that, according to America's finest news source, we have the highlight of the scientist's testimony was a series of several colourful diagrams of how the big machine would work. One consisted of coloured dots resembling skittles banging into one another. Noting the motion lines behind the circle ball things, committee members surmised that they were slamming together in a, quote, "fast, forceful manner." Yet some expressed doubts as to whether they justified the $50 billion price tag. "These scientists could trim $10 million if they would just cut out some of the purple and blue spheres," said Representative Roscoe Bartlett, explaining that he understood the need for an abundance of reds and greens. Quote, "With all those molecules and atoms going in every direction, the whole thing looks a bit unorganised, especially for science." Now, I mean, Brian gave a very wonderful introduction without the need for the kind of visual aids and so forth, and I don't think the satire reflects on the efforts of scientists and physicists to talk about their work to the public, that I think often they kind of do a very good job over. But what I think it does draw out is the kind of philistinism in particular of the kind of political class, the policymakers, the funders of science, and draws out the sense of the concern for national competitiveness, the concern for cost and so forth, where the concern for the advancement of ideas is pretty much absent. Now, if it wasn't the end of the weekend, maybe I'd quote the real-life version of the Onion that you can read in the Sainsbury Review of Science and Innovation. You can find the press release on the kind of 5th of October with Chancellor of the Exchequer, Alistair Darling, and Secretary of State for Innovation, Universities of Skills, John Denham, and so forth, kind of making not such dissimilar kinds of points. well, maybe I will quote a little. You know, the Sainsbury Review of Innovation, which is the kind of new vision, says, presents the vision for a new science and innovation landscape for Britain. We're going to take that step of vision further. We're making good progress, but so are our competitors, and we need to keep the UK ahead of the game. And even more, this is what the Chancellor of the Exchequer thinks of science. The UK can only maintain its competitiveness in today's more globalised world by placing itself at the forefront of the new scientific and technological breakthroughs that determine the future face of our economy. This government is already investing record levels in the UK science space, with the transfer of knowledge into the private sector significantly improved, right? So, you know, they're kind of ticking all the boxes there in terms of knowledge transfer, the kind of fairly narrow vision of what it is that we're going to kind of get out of science here. Now, I guess I could, if we've got a few minutes left, give an attempt at an alternative kind of sense of the kind of project that I think that particle physics is engaged in, really, and a sense of kind of where it's coming from. You know, I think to me the kind of origins of this, you know, if you go to the Vatican, to the philosophy section of the old library of Pope Julius II, and you look up, you can see a very wonderful famous painting painted by Raphael in 1510 entitled The School of Athens. And spread across the steps of the School of Athens are all the famous ancient philosophers who the Renaissance Italians thought were the great masters who they couldn't move beyond. And you find Plato there in the centre looking up to the skies, pointing upwards because he thinks, you know, ideas are the key. You've got Aristotle there kind of pointing downwards towards the earth, observation and so forth. And it's really the conundrum of how to reconcile these things that had held back science ever since the Greeks. And you find 50 years later, after the Renaissance, born Galileo Galilei, who moves things on by essentially inventing physics, and inventing modern science in the process, by reconciling this balance between theory and experiment, by finding the kind of dynamic balance between them. Beginning his investigations through investigating the motions of particles, the laws that determine these things. Then leading on, you know, inspired by Galileo, you find Newton, his name associated not just with, you know, a scientific revolution, many breakthroughs are labelled with that, but the scientific revolution. You find Newton taking this idea of looking inside, looking at the motion of particles, breaking down, going smaller. You find in his queries at the end of his work on optics, describing how the properties of fluids, of solids and so forth, can all be described by the interactions of these smaller particles, laying the foundations of chemistry. You know, you find the tradition carried on by chemists and physicists through the 17th and 18th century. You know, at the end of the 19th century, you have Mendeleev clarifies the notion of atom, lays out the pattern of all the atoms in the periodic table. You know, a conundrum, as Brian described. You know, here's all the particles, what's behind them. You know, in investigating the periodic table, all the different chemical elements, you know, that laid the basis for the modern physics, for quantum mechanics, for the inside of the atom, for the electrons and nuclei and so forth, everything that Brian described. You can see there how productive it's always been to go further, go deeper. And, you know, today we're presented with this same pattern. We don't know whether the new pattern we've got, the new mysteries, are going to be resolved by finding something inside them, whether there'll be strings, whether there'll be some kind of new explanation altogether. But I do think that if we see ourselves as part of a continuing quest to understand nature and to kind of move forward and kind of take forward that quest, which, you know, every previous generation of scientists had to kind of try to scrape together resources from one place or another. You know, today with kind of modern resources, modern economic growth and so forth, we have the capacity to invest in this stuff, and rather than seeing particle physics as something that should potentially contribute toward economic growth or pure science, I think we really want to start looking at these things the other way around and say that modern growth should really justify itself by contributing towards the investigation of nature and science and the Large Hadron Collider. And I think if we can develop a bit of that spirit, then we'll ensure that both the Large Hadron Collider will be a success and we'll have a successor.
Thank you very much. Who said physics was boring? If you were in the last session, you know why I get upset, but there you go. I'll throw it open, but it's worth thinking of a very simple question in terms of how we look at this. Because from people who don't get this stuff, they're just going to ask, what's it all about? What's it for? What use is the Higgs boson if we do find it? So that's my question. Right, we've got microphones, we've got a couple of people. You first.
Hi, just a couple of questions really. The first one, do you think that scientists have a moral responsibility to explain their research to the public, in the sense that is science publicly accountable? And if there's not a strict moral sort of obligation there, do you think that scientists owe it to the public in some way to explain what they're doing, and how should that happen? I think it was very funny, I got for Christmas once a book by Stephen Hawking, A Brief History of Time, which I half read and went on my bookshelf, and I did hear, I heard that a lot of people actually bought this book, but nobody read it. It was that kind of, I've got this book, I understand what's going on, but obviously nobody really did. So I mean, at what level should that communication come, if it does come? And just a third sort of comment, which is, I'm quite interested in what you say about this concept of mystery in science, and I think that's very important, and it kind of seems like that's something that perhaps has been lost in contemporary society. I mean, it's absolutely fascinating. You kind of sit here and think, shit, we don't know anything about the world. And I just kind of wonder how that's got lost and how that should be recommunicated.
Okay, we'll take a couple of questions and I'll ask people to respond. So, you, sir, and then him.
Thank you very much. Just 2 points to make. I first heard of the Large Hadron Collider earlier on this year, and at first I was confused because I misread it as Large Hadron Collider.
That's what Microsoft spell checker turns it into. You type in hadron, it changes it into hardon. Colluder. Large Hadron Collider, it makes it.
My first question was, do you think a possible renaming of the Large Hadron Collider could help make particle physics even sexier? My second point, on a more serious note, names, is it Joe? Yes, Joe mentioned that he thought scientists were very good at communicating to the media and public what they're doing. I beg to disagree. I remember when the dark matter story broke, people's general opinion after reading about it in the paper was, thank you very much. What does it all mean? It's all a bit confusing. String theory, it sends people cross-eyed. How can you communicate this to them effectively so they realise that you're not just messing around with money and large things under mountains, which have phallic names, but actually doing something that's going to benefit them in the end?
It was you. No, wrong way around. You, sir.
I have a simple question and a point, which is, perhaps, Joe, you would like to say more about Galileo and Newton specifically in relation to particles, because in most people's estimation, or at least mine, particles is not what they're known for. But I will, and so I'm not talking about the movement of Jupiter's moons here, right, or apples. I'm talking about particles qua particles. And what I can say is Einstein's paper on Brownian motion in 1905, the annus miraculis of everything really in 20th century science, is one of the most neglected but most important pieces of the jigsaw in exactly the very eloquent spirit that Joe Kaplinsky demonstrated.
take you, and then I'm going to ask you both if they want to make a comment.
If you look at research in chemistry or biology, it's often fairly obvious what the benefits are, and I think we're all very pleased that we got the America got the nuclear bomb before the Germans did. The great white hope was nuclear fusion was going to give unlimited power, whatever. That seems to be some way off now. Can you actually say some concrete examples of things that are like benefits that are likely to be achieved? So what we will get for the large amounts of money which we're spending on nuclear research.
Fair enough. That's the nuts and bolts question. Do you want to have a go?
So, yeah, to the first question, this idea of mystery is really important, actually. I think it goes back to the first two questions you asked about communicating to the public. I really see science as exploration, and I see research science as the act of going to the edge of our knowledge, right onto the precipice and looking out into the dark and trying to find out what's there. I see it as nothing, in a sense, nothing more than that, right? That's the essence of science. And often when you find scientists accused of being dogmatic and somehow protecting some edifice of science, I don't recognise that at all. I really do agree with you that if you can get across the fact that it's the same as going to the moon or going to the Mars, or just crossing the ocean, it's all about going to the horizon and trying to find out what's there. And I think that's what humans do. It's almost what humans are for, in a way. And I agree with you. I agree that there's a moral and every possible obligation for communicating to the public, not least because they pay for it, but also because I think it's like art and like literature. It's one of the things that makes it worth living in the first place. Finding out about the way the universe works. I think everyone's got a right to know about that. So I wholeheartedly agree with you. Then there was your question about particle physics. I mean, there's a wonderful speech made by a physicist called Casimir, we were just talking about it earlier actually, who ended up being the research director of physics, which is a theoretical physicist. And he made a very powerful speech defending fundamental research and gave loads of examples. He said, for example, the transistor. It could have been invented by electronic engineers who were trying to miniaturize electronics, but it wasn't actually. Transistors were invented and the basic physics was understood by people who wanted to apply quantum mechanics to silicon to work out how it works. You could have invented the electric motor by deciding there was a need for efficient transport, or the generator because you didn't want to have gas lights, you wanted to have electric lights. That was not why it was invented. It was invented because people like Faraday messed around with bits of wire. You could have say, he didn't say this because he died by this point, but you could say the World Wide Web would have been invented by Microsoft. May well have been, but it wasn't. It was invented by physicists at CERN because they wanted to move data around. You could have said that medical imaging would have been invented because it was useful and a good diagnostic tool. It wasn't really. MRI imaging is a direct spin-off of understanding something called spin in quantum mechanics, which is, again, a product of trying to understand the basic building blocks of the universe. And I don't think it's surprising, because I think that if you try and understand how nature works at a fundamental level, then technologies will emerge. And I think it's impossible to direct it.
Thank you.
Yeah, well, I mean, just on that, I think it's true that out of basic investigation of the world, you're going to produce technologies in a way that's unforeseeable. And furthermore, the larger the technological impact, the harder it is to kind of foresee those consequences and possibilities. But, I think we've really got an opportunity today, which I was kind of trying to allude to perhaps at the end of my remarks, to go a bit further than that, because if you look at the motivation for funding of science in the past, that's either come from industrialists or the state and so on, they've always had an interest, for example, very often military in physics research and so on, all the way from Galileo through to kind of modern nuclear research. There's kind of been that kind of military interest on the part of the state and so forth, rather different to that of the scientists. With modern society, I think what we want to actually celebrate is that for the first time in human history, right, we have the possibility to actually dedicate resources to the pure investigation and development of knowledge. If you look at kind of economic growth today, as kind of generally people are fairly kind of begrudging about defending it. It's like, maybe the Chinese, well, they're poorer, so we have to kind of allow them to have some growth, even if it's kind of making us all kind of feel sick in the West. And you have to more or less go to kind of maybe a Malawian peasant before you kind of find people, oh yes, it's kind of, we can feel happy defending growth there because they're poor and so on. But people have a feeling that, you know, wealth for us in the developed world, what's it all for? You know, buy kind of, 3 more cars, it's, bigger house, it's all kind of terrible thing. I think, we can actually say that there is something, there are great things that we can do with our wealth. There's no need to be embarrassed about the fact that we want to spend it creating laboratories, like CERN that can go off and investigate the world, right? We want to celebrate the fact that for the first time in human history we can go and do that because, as Brian rightly puts it, I think, this is an important part of what it is that makes us human. And I think it's, it's a great chance not to be defensive about that at this kind of moment in time. Why would we turn our backs on that when this is the kind of the first time in history that there's enough wealth to go and do that, and suddenly we get kind of wrapped up in what's the justification?
Okay, thank you. Right, we've got a fella there, and there's another one, young lad there. If you can come around here for a minute.
Just wondered, I watched the BBC 4 programme recently with the bold physicist.
Jim Al-Khalili.
Right. He, pardon my ignorance, but he portrayed the debate between those who thought you could visualise the world and those who disagreed that it was possible to visualise. I think I'm right that there was that debate. Given that this is about sexy, and I'm trying to think sexually, and if you agree I should visualise, how could I visualise physics in that way? I mean, obviously I'm interested. Do you want? Are you in favour of visualising it, and how should I visualise it as being a bit ignorant? And secondly, this is just that's for both of you, but this is for Brian. As a teacher myself, you seem quite young. Are you a bit of a young Turk in your field? And how did you get that? Did you have an inspirational teacher, or do you think you were born that way, or was it came from your musical interest in things that can only get better, or where does that all come from?
I could just answer. I want to quickly answer the second bit. I was born in time to see the moon landing, which is one of the reasons that I think I went into physics in the first place. And Carl Sagan was one of the guys that really motivated me to go into physics. Cosmos, and I recommend that if anyone hasn't seen it or read the book, do it. So it's great communicators. I could get the second bit after the question.
Isn't it a kind of inevitable consequence of the progression of physics, kind of further away from intuition as time goes on, as it appears to be doing, quantum theory and so on? Isn't it an inevitable consequence of that it's going to become harder and harder for the public to understand modern theories and ideas, and beyond the point, perhaps they should stop pretending that they can grasp them and just leave the scientists to get on with it, as it were?
Ooh, I want to answer that one, but no, I'm not going to. There was, this gentleman here, and I think there was, did you want to? Yeah, afterwards.
Just a point of information, a person before asked what did Newton do for particles. It occurred to me that he did seem to realise that to explain light you needed the concept of the particle and the wave. That was about 1700, and it wasn't realised till 1900 that he was right.
That's right.
Since we're talking about sex and being sexy, and Brian mentioned how we should be able to communicate the excitement of a journey, but I think unfortunately what physics tends to do is excite geeks like myself and a few others who get excited about string theory and can't really explain. I certainly find it very difficult to fully understand myself and pass on to other people.
Probably because it's bollocks. Another sexual message.
I didn't want to say that, but I'm inclined to agree. But if obviously you're trying to justify a huge spend, both in terms of capital expenditure and running costs. Is it 135 megawatts?
That's right.
Draws? It's quite a lot, and quite expensive. Taxpayers will want to know why why they're spending so much. And spin-offs are certainly one argument, and certainly they have to be made clear that there are a good number of spin-offs. There's a good amount of employment, and that also should be mentioned. But in order to portray it as a voyage, something else needs to be done. I think people relate to, ordinary people, not scientists, relate to other people. If you're in a rock band, they relate to the players, they relate to the stars of the rock band, they relate to Phil Collins or whoever. That's my generation. But going on too long, haven't I?
Just because we're going to run out of time
Before
any
Joe
moment.
gets a chance to answer, can I just say one quick thing about the cost of it? Because I was talking to some of the CERN guys the other day, and it's actually remarkably low cost. In fact, it has less budget per year than a medium-sized university. And this idea that you should have one medium-sized university in the world that's concerned with understanding the fundamental building blocks of nature is really quite obvious to me. The budget is about less than a billion Swiss francs a year. It's about 400 million pounds a year. Flat budget, it does everything out of that. That's contributed basically by every developed government in the world, but certainly the governments of Europe. So I think it is remarkably cheap, actually.
But let's have a rock concert in support of CERN.
Right. This young lady here, and then I think, we've got two more. Then two more, and that's it. Right, go on.
Well, it's obviously between, say, science and the public, there's the media is used in between, and it comes across to me quite a lot that media commentators tend to be the type of people who probably didn't enjoy physics at school, and who are quite flippant about it, and their kind of rhetoric is usually quite against and makes it sound difficult when people could understand it. And do you think there should be more people, such as yourself, Brian, who are good at explaining these things and are good communicators out there, getting people excited, really? Because I know in the scientific community there can be people, it's like, well, we want to get on with our job, because scientists, they can see why it's important and why it's good and why it is exciting. And it's a case of taking a step back and identifying people who could be good at communicating it straight through and not through the usual media commentators.
It is interesting that if you look back in history, I'm not trying to decry Brian's fame or anything, but Albert Einstein did it better. When he tried to explain his theory of gravity, which nobody really understood, he was a complete superstar and got popularity much bigger than at the moment that we're seeing coming out of the idea that CERN's going to produce something. Maybe that will change. Maybe Brian or whoever, or Peter Higgs, if he's still knocking around.
He is.
He might make it onto the world stage or something like that. But at the moment, it seems that we've lost that kind of response to science. And it's kind of a funny thing to try and want to recreate it is missing the point about why it's gone. And I think that's one of the things that you're sort of trying to work through is what has happened to science and our perception of it. You, sir.
Just
ignore that. Go
on. In response to this this bloke down here about whether science should be left to scientists and those who specialise in it, because one of the things that I forget which scientist, but he was one of the people involved in the development of quantum theory, and he said that new ideas don't emerge through the sort of refutation of the old ones and people just giving up the ghost on them, but rather you've got a generational shift where the people who come into it and learn the new stuff just accept it and take it as part of their common currency. And the point about new ideas in physics is that those who've been steeped in the old ways are going to have much more difficulty in abandoning their preconceptions than the people who obviously have come in and they're well aware of all the new stuff and they don't carry the same baggage. So those of us that strive and have got an interest in these things should keep pushing the barriers and try to grasp things that are very difficult for us, because the consequences of that is that the people who come after us will find it that much easier.
I agree.
Did you want to say something?
Just quickly, the person over there made a point about how physics is getting more and more divorced from common sense and reality. I'd just like to say that physics never had anything to do with common sense. I mean, if you look at the world around us and try and think about how it works in common sense, you end up with a world at the centre of the universe in which things revolve around it.
Okay, fair enough. Right, I'll ask you to make your final comments. We're completely out of time, but we finished on time. So, reverse order, is that right?
You haven't said anything for a while.
Yeah,
right.
Okay. That's all right. I'll try to tidy up a few things in one sentence replies. Okay, at the back there, Newton on particles. If you look at optics, is query 31. As I said, he tries to explain how, the stuff that we see around us can be explained by the motion of the particles inside and the interactions of those particles. And I think that's the kind of in a line with the quest we're on today. On the are the public too stupid to understand physics nowadays? Well, if you look at the public in general, they're getting cleverer. You can look up something called the Flynn effect. The average IQ rises, and they disguise it by kind of resetting it. So, I think the public is cleverer than we maybe give them credit for. On string theory, all these wild theories, I guess it's back to Galileo and the balance of theory and experiment. And, this is why we need the Large Hadron Collider. And, maybe it's because the superconducting super collider was cancelled all that time back that we're desperate for the experimental side of things to kind of balance things out. And the last word I'll give quoting Bob Wilson, who was the director of Fermilab, a particle accelerator in the US. And he was asked by a congressional committee, what will your lab contribute to the defense of the US? And he replied, nothing, but it will make it worth defending.
Ryan.
Just one very quick point I think that hasn't come up. I really believe that fundamental physics, indeed fundamental science, is not a luxury. I really think that it's essential in order for our species to survive at all. I mean, there's a very famous quote, if we're ending with wonderful quotes, I love that one from Wilson, that there's a great quote by Carl Sagan, who I'd said was one of the guys that got me into science in the first place. He said that if the dinosaurs had a space program, they'd still be around, right? Which is kind of funny in a way, but actually quite profound. It's actually true. And this idea that the universe or the world outside our little planet is not necessarily benign, right? It can be quite a dangerous and violent place. Mass extinctions occur quite regularly. We're the first species on the Earth, and possibly, as far as we know, the only species in the nearby universe that has the power and the potential to be able to deflect nature when it causes these problems for us, but only if we continue to try and understand it. And I think this sense that if we just sit by and we're careful on the Earth and we don't put CO2 into the atmosphere and we'll be okay because we feel safe, I think that's really wholly wrong. And I think that you can justify fundamental research purely on that level.
Thank you.